All right, we are covering 3.6 rational functions. In this video, we are covering the first part, which deals with the asymptotes. Okay, so take notes. Rational functions. Rational, keyword ratio there. So we're talking about functions that are fractions of polynomials. So you have a polynomial over another polynomial. Okay. All right. So rational function. A function of the form p of x, so that's a polynomial, over q of x, which is another polynomial. So a polynomial over another polynomial. Okay, so where p of x and q of x are polynomials. Okay. And because we have this fraction, just like rational functions that you looked at in the past when you were asked to find the domain, it still holds here. We don't want 0 in the denominator. Okay. So your domain will be all real numbers. All real numbers except those that make the denominator zero. Okay, so for example, if I have something like this, g of x equals 2x minus 1 in the numerator, and then x plus 3 in the denominator, then the domain here is all real numbers. All real numbers except -3, because we can see here, if x is -3, -3 plus 3 is 0, and we get 0 in the denominator, which is undefined. Okay? All right, so asymptotes. Oh, let's back up over here. So I spelled this all out. If you're going to use set notation, all real numbers except for -3. So that would be like this: -infinity to -3, and then -3 to positive infinity. And we use parentheses here because if we use the bracket includes -3, but we're trying not to include -3. Okay, asymptotes, a line to which the graph of the function gets closer and closer to as one travels along that line. Here, I'll draw you a visual of this. Okay, so for example, You might have something that looks like this. Here's your graph. Okay. And maybe you have a horizontal asymptote, this horizontal line here at 1. And maybe you have a vertical asymptote over here at 2. And your graph behaves like this. And like this. Hold on. Trying to extend this if it's long enough. Oops. All right, so suppose that it does something like this. Okay, so what they're saying is so as you travel along that line, so like let's say I'm traveling along this line, right? As I travel along this line, we see that this graph gets closer and closer and closer to this line. Okay. Same thing with this one. As I travel along this line, this graph gets closer and closer and closer to it. Okay. Same thing if I go in this direction and traveling along this direction of this line, I see that this graph gets closer and closer and closer to it. And the same thing with this line. As I travel downward, I see that this graph gets closer and closer to that line. Okay, so these are the asymptotes. Okay, these dashed lines are what we call asymptotes. This one here is the horizontal asymptote. And this one over here is the vertical asymptote. Okay. All right, and what we're going to be doing here is we're going to be looking at how to find these if you're given a rational function. How do you find these asymptotes? Okay. All right, so let's take a look. The vertical ones are pretty straightforward. All right, let's take a look here. Finding asymptotes. All right, so if you're given this rational function, we'll call it r of x, which is, so it's a rational function, so it's made up of a fraction of two polynomials, p of x over q of x. And let's suppose that p of x is some polynomial a n x to the n plus all the way down to a0. And let's suppose that q of x is some other polynomial bm x to the m plus all the way down to b0. Okay. All right, so then your vertical asymptotes, we'll start with those. Okay, so these occur at x values that are not in the domain. So basically, where the denominator is would be 0. Okay. where denominator q of x equals 0. Okay, because those values, those x values are not part of the domain, right? And so what happens is, since they're not part of the domain, then that means that you're not going to have a point of the graph at that location, at that x value, right? You're not going to have a graph, a part of the graph there. And so what happens is, in this particular case, you will have, instead of a point, you will have a vertical asymptote, okay? So let's take a look at some examples. Suppose that r of x equals x over x minus 2. Okay, so we can see here that the denominator would be 0 at x equals 2. Okay, we can't, so x equals 2 is not going to have a point on the graph. Okay, so the vertical so here you have a vertical asymptote at x equals 2. Okay, so what happens is, when we start to graph these right here at x equals 2, you are not going to have a point on the graph there. Because if you use 2, you get undefined, right? So right here, there is not going to be a part of your graph, okay? Your graph will not cross this line, okay? And that's the difference too. One of the differences between the vertical and horizontal asymptotes. Vertical asymptotes, your graph will never, ever cross it, okay? Because that's where your function is undefined. Right here, x equals 2, if you plug in 2, you're going to get 2 over 0, which is undefined. Where do you plot undefined? Nowhere, right? Okay, so vertical asymptotes, your graph will never cross. Okay, let's take a look at this next one. Suppose that your rational function is x plus 3 over x minus 1 times x minus 3. Okay, so then here we want to know when the denominator is 0, right? So we set each one equal to 0, and we solve. Add 1 to both sides, we get x equals 1. Add 3 to both sides, and we get x equals 3. Okay, so that's where you have vertical asymptotes. You have vertical asymptotes at x equals 1 and x equals 3. Okay, so when you graph them, 1, 2, 3, you'll have one here at 3, and you'll have one here at 1. Okay, and let's take a look at one more. Suppose that you have this rational function, 4x minus 1 and 2x minus 1 times x plus 5. Why don't you go ahead and hit the pause button and see if you can find the vertical asymptotes for this one, and then come back and check. Okay, so right here, set each factor equal to 0. Solve each one. X equals to 1/2. X equals to -5. So that's where you have vertical asymptotes. You have vertical asymptotes at x equals 1/2 and x equals -5. Okay, so -1/2, no, 1/2 And 1, 2, 3, 4, 5. Right here at -5. Okay. All right. So vertical asymptotes, those are generally the easy ones. They're both easy, vertical and horizontal asymptotes. They're pretty. They aren't complicated to find. Um, so vertical asymptotes, they occur at the x values that are not in the domain. So that's where the denominator equals 0. Okay, so let's take a look at horizontal asymptotes. Okay, so here, this one's a little more complex. So what you're going to do is you're going to use the leading terms. So you're going to use the leading terms of P of x and Q of x. Okay. And so that would be we look back up here. That would be this one and this one, right? These are the leading terms of the two polynomials. Okay. All right. So that would be a n x n and b m x m. Okay. And then use the following. Use the following rules. Okay. All right. So if n is less than m, we have a certain situation. If n equals m, we have another situation. And if n is greater than m, then we have a third situation. Okay. All right. So let's take a look at this first case here. So n is the degree. So we see here it's the degree. So if the degree in the numerator is less than the degree of the denominator, if n is less than m. So if n is less than m, then you have a horizontal asymptote at y equals 0. Okay, these are horizontal lines, and horizontal lines, the equation of a horizontal line is always y equals some constant. Okay. All right, if n equals m, so if they're both the same degree, so if you have x squared on top and x squared on the bottom, then you have a horizontal asymptote at y equals the leading coefficient over the leading coefficient. So if you have 2x squared on top and 3x squared on the bottom, then you have a horizontal asymptote at 2 over 3. Okay? We're going to look at some examples, so just hold on a second. If n is greater than m, then there's no horizontal asymptote. You actually have something else called a slant asymptote, but we're not going to cover that here. Okay, so let's take a look at some examples. We'll take a look at these cases here. All right, so suppose that we have r of x equals 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. Okay, so here we have that they are the same degree, so n equals m. So we have a horizontal asymptote at leading coefficient over leading coefficient. So that would be leading coefficient over leading coefficient. So we have a horizontal. Here, let me do this. So this one is degree 3. I mean degree 2. And the denominator is also a degree 2 polynomial. And so therefore, we have a horizontal asymptote at y equals 3 over 2. Okay, you have to use the leading coefficient. If they're the same, it's 3 over 2. Okay, let's take a look at another one. Suppose that I have this here, 3x over x squared minus 4. Okay, so up here, we have a degree 1. And over here, we have a degree 2 polynomial. Okay, so up here, it's smaller than here. So that's this first case. The degree in the numerator is less than the degree in the denominator. So then it says you have a horizontal asymptote at y equals 0. Okay, so those are basically your two choices. If it's the same degree, you'll use the leading coefficient over leading coefficient. If it's a smaller degree on top, then it's just automatically at 0. Horizontal asymptote at y equals 0. Okay? Because the third case, you don't have one. Okay? If it's larger degree on top, there is no horizontal asymptote. All right, go ahead and try this one. Here, I want you to do this. Find the vertical and the horizontal. If they exist. You might not have any, right? Okay, here's your polynomial. R of x equals x squared minus 9 over 2x squared minus 13x plus 15. Okay, go ahead and find both the vertical and the horizontal asymptotes. Hit the pause button and come right back. Okay, so the vertical, let's start off with that. Vertical. Okay, so we have those where this equals 0, the denominator equals 0. All right, so I'm going to go ahead and see if I can factor this. 2x minus minus 5 and 3. 5 will go here, 3 will go here, and that will give me negative 13x for the middle. All right, so this one, I get x equals positive 3 over 2. And over here, I get x equals 5. So this is where I have my vertical asymptotes. I have two of them. One at x equals 3 halves and one at x equals 5. Horizontals, same degree. They're both degree 2. So I'm going to have it at y equals. So remember, verticals are x equals, horizontals are y equals. Y equals 1 over 2. Okay, so remember when they're the same degree, use the leading coefficient 1 over the leading coefficient. Okay. All right. Excellent. So here, if I were to start graphing these here, I would have verticals at 1.5, 1.5. So I would have a vertical here, and 1 at 5, 1, 2, 3, 4, 5. So I would have those two verticals, 1.5, 5, and then I would have a horizontal at 1/2. So right around here. Okay, so those are just the asymptotes, but that's the beginning part of the graphing. You will need to find out where you have your vertical and horizontal asymptotes. You would put them on the graph, and then the actual graphs will be in here, and we would need to make a table of values to come up with the general behavior of the graph. Okay, so that's part 1, vertical and horizontal asymptotes. If you have any questions, make sure you message me.